Hi, welcome to Module 7. Module 7 is basically about metrology, its principle and its system and application surveying. We are going to discuss first the terminology, what is metrology. We then discuss the component of the precision surveying and specifically industrial metrology that is more useful for us as a surveyor. And then we are introducing different equipments that is currently used in this area, and then at the end we're hoping that you understand the principle and techniques and to be able to do the decision making and use this instrument to achieve the certain requirement accuracy. What is metrology? Basically, metrology is the science of measurement. We want to measure the devices or industrial machinery, or it can be the ship, aircraft. So the measurement here needs to be very precise, let's say better than 1 mil at 95% confidence level. So this is the general or more simplified version of the metrology. But if I want to really tell you what is metrology defined, is basically the science of measurement, embracing both experimental and theoretical determination at any level of uncertainty in any field of science and technology. Metrology can be divided in three basic overlapping activities. First, it can be used for defining the international fundamental metrology, or theory is mostly scientific and theoretical metrology. The next one, which is the one we're interested in, is the application of metrology to engineering, industrial and technical aspects mostly. And the last one is basically linking the measurement and make sure that our measurement meeting the reference standards. This can be applied, for example, if you are measuring the machinery, make sure that its dimension is meeting the specification or requirement for that machinery. Here we want to focus mostly on the large scale dimensional metrology, or we call it LSDM. Basically, this type of metrology is for measurement of anything within 5 meter to 500 meter distance, and we want to achieve the accuracy of 1 millimeter at 95% confidence level. So see, the precision is very important, so I highlighted this. So far in the surveying you might not have anything better than this. That's why we introduced the metrology. Metrology, you can achieve the very precise accuracy, say micron meter. So if you're measuring in the short distance, basically we can ignore the curvature of the Earth's gravity and anything regarding to the ellipsoid approximation that we are using in normal surveying techniques. The principal drivers in large-scale dimensional metrology is basically can be divided in 5: scale, complexity, distribution, time frames, and robotic. Talking about the scale, first of all, the object we want to measure in large scale metrology is very big, like big machinery, like aircraft, like ship, and the scale become larger and we are demanding a very precise measurement. The next one is complexity of the surface. We no longer have a very defined and basically very simple surface. Most of the surface we are dealing with in metrology is very complex, like a surface of aircraft, spacecraft, missiles, high-speed trains. All those are the examples. Distribution. Basically, distribution comes with the fact that the manufacturer mostly they outsource the component, like many of the components of the Airbus or any aircraft will be manufactured in different parts of the world. So it's very important that we make sure that all the parts has the consistent accuracy. We're also looking at the shorter time frame. We want to have anything in real time on location and very fast. And the last one, which is a demand for large scale metrology, is the increasing use of robotic manufacturing system. Bring the need to calibrate and monitor the robotic system, make sure that they can measure like 3D with very precise accuracy. Relative precisions and uncertainties are critical in large-scale dimensional metrology. This table shows the uncertainty in a generalized form, ignoring the environmental condition and other errors. So you can see here we are looking at the measurement uncertainty of the EDM, angle pointing, and GNSS with regards to the distance. So EDM here, I use the standard instrument in the market, let's say Trimble S7, so it's going to be 1 millimeter plus minus here 1 ppm or part per million time distance. So you can see I will show you the very first one and last one to show how we calculate that. Let's say the EDM, we want to see what is the sigma, and we know the sigma is at 68% confidence level. So let's calculate the sigma for the 2 meter distance. It's gonna be 1 millimeter plus 1 times part per million 2, so it's very small and it's gonna be still 1 millimeter, so it doesn't change the accuracy that much. But if I'm doing for the 5,000 meter, it's gonna be 1 millimeter plus, sorry, so this one comes to 5 millimeter, and it's gonna be sigma is 6 millimeter at 68% confidence level. This is the ratio, so it's basically part million this bit here, and this is ratio at 95% confidence level. We all know that it's roughly divided by 2 or divided by 1.96. Same thing for the angle. Angle pointing is 0.5 second of arc for one pointing, and is the inverse or proportional to the distance. So as we further pointing to the object in 5 kilometers, you're never gonna get the same accuracy at 2 meters, so it's getting worse. The GNSS is a little bit different. GNSS is the error introduced by each station, so it's plus and minus 5 millimeter per station. So to measure the distance, we always have 2 stations, so using the error propagation formula, we can have this one, which is roughly 7.1 millimeter uncertainty in the distance. So you see that GNSS accuracy is not changing over the distance because it's irrelevant. This is a decision making for the metrology system. You can see we need to consider different options like the site geometry, equipment, site condition, atmospheric condition, like thermal limitation. Then we need to know what are the skills needs, whether it's the high skill or we can simply do it by have a quick look or training, or is it the instrument we already used. So object, whether object is complex, is big, small, so it's really changing the what we need to use for that application, and also what is the tolerance or accuracy we need to achieve, and at the end what are the math model we want to use. So these are the considerations you have to always whenever you are doing anything for large scale metrology, you have to look at all these conditions and terms and make a decision based upon that. In Metrology, we do have different terms that you haven't seen probably in different courses we had in surveying. We're talking about the very precise measurements. So we have right now we know about the meter, centimeter, and millimeter, but in this course we're talking about micrometer, micron, nanometer, and also in terms of the time measurement we are looking at the millisecond, microsecond, nanosecond, and so on. Large scale dimensional metrology deal with the measurement of an object with a specific environment and location. So we have to remember there is always a constraint with the scale, shape, and orientation of the object. Having said that, we can categorize the method in metrology in three different categories, like measurement space of the large scale dimensional method metrology, general measurement mathematical models, and microgeodetic networks. I'm going through each of them individually and explain what are these. Let's start with the measurement space of large-scale dimensional metrology. In this method, we are looking at a three-dimensional space which is defined by x, y, z, or the coordinates of the point, and we are looking at the vector. So if we are talking about one point, it's only the coordinates defining that point. Vector is obviously a combination of the 2 points in 3D space, and if we are looking at the surface, it's basically 3 points create a plane or a surface in 3D space. We also have the complex surface, which is not really simply by 3 points. It's very complex, and it can be defined by mathematical formula, and it's basically a combination of the points, lines, and planes, which is this example show you different or show you an example of the complex surface. Another thing we have to remember in measurement space of the LSDM is rotation. If you're talking about the two-dimensional space, rotation of the two-dimensional object can be shown by only one element. So we are talking about the 2 dimension. But if we are talking about the 3D space, we always have, like what you've learned in photogrammetry, we have pitch, roll, and yaw, which is the rotation around 3 axes of x, y, z. So in larger scale dimensional metrology, we have a term we call it volumetric accuracy. Volumetric accuracy is the way we express the precision in the metrology. This is the relatively new term, and basically shows the move from a single plane or line. It can be the examples of measuring the alignment, flatness, all those are the examples. And we are looking at measuring the 3D coordinates of the point in space, which basically we can measure it as an absolute coordinates or relative to a specific datum points on the object. So it can be relative or it can be absolute coordinates. So how are we going to define the point in the 3D space? Usually using the vector from a datum point. So this is the datum point and this is the point we want to measure, and then we can express the vector using the cos of the rotation or angles in respect to the x, y, z. So this is how they express the vector in the math. You don't need to know too much of that. It's just the introduction that how we measure the vector in metrology, and basically instrument does this for you. It's just understanding the concept of that. So I told you about the measurement space. Now we want to move to general measurement mathematical models that it can be used in metrology. So it can be categorized as a measurement of the single line. We call it alignment. We may want to measure the angles only distance or radiation, or we want to measurement through intersection of the planes. We also are going to talk about the object space versus measurement space compare them together, and we always like to have the redundant measurement for the adjustment purposes, and it gives us more confidence. So I'm going through each of them individually, and we want to see how we are mathematically model different measurement in metrology. Measurement of a single line or alignment. To check an alignment, we need to first have a reference line, or which can be basically done using an optical sight, or a laser beam gives us the reference line. And then we are measuring the distance from the plane or the surface to this line using the precision scales. So we measure the offsets at an interval of, I don't know, 10 meter, 5 meter, depends. And then this gives you the opportunity to measure the horizontality of the surface, or in some cases the flatness of the surface. The next one is measurement of the angles only. Measurement of the two angles, as we know, in 2D space, define a point. So if I know the coordinates of the point A and B, and I know this angle, this defines a point P for me. But if you want to have that point defined in 3D space, you have to measure the three angles, but also we have to know the baseline, which is in this case A to B. So we have to know the base coordinates, also the orientation length of the base, to be able to define that point in 3D space. Radiation is another method of defining the point. From what we know from surveying A again, if I know the length of this vector, I know the vertical angle and horizontal angle, I can define the unique point of the P in 3D space. Measurement of the distance only, which is trilateration. Again, we know it from the comps-in survey. We discussed the resection and trilateration. If you know two known points and you know the distance from that 2 points, you can measure the point in 2D space. Obviously, if you want to define a unique point in 3D space, we need to have the three distances, and the points should be all in one plane or one surface. The next one is measurement through intersection of the plane. If you have two known planes that define the line, so if you intersect two planes together, that define the line for you in the space or 3D space. If you have three planes, obviously you can have a unique point which comes with the intersection of those three surfaces. The objective space can be used if we have minimum 3 known points. So if you want to use objective space and get the coordinates directly, you need to have minimum 3 known points, and then you are measuring everything in object space coordinates. But if you want to use the measurement space, you need to have the 6 degree of freedom. By 6 degree of freedom, I mean X, Y, Z, pitch, roll, and yeah, I think. I'm not quite sure about the symbols, you better check them, but I mean rotation around 3 axes. And then there is sometimes 7 degree of freedom if you're monitoring the movement of an object, or say in deformation surveying or monitoring, we always have a time component adding to this, which comes to the 7 degree of freedom to be able to measure one point in the space. Like any other surveying techniques, metrology is very much rely on the redundant observation to improve the accuracy and driving the unknown parameters. We usually use the least square technique to achieve this. We have to be careful that this algorithm should be efficient and convergent, and it should be in real time, because most of the time we need to have the coordinates and everything in real time and on the fly, what they call it. Microgeodetic network is very important and critical in large scale dimensional metrology. The method used for this type of network is pretty much the method we are using for the large scale surveying. If you know about the geodetic network, we have triangulation, trilateration, radiation, resection, combination of these methods to establish the network. We are using the exactly same thing here. The only difference is the geometry of a site and target location are critical to establish in the macro geodetic network. Once we establish the network, we are using the least square adjustment to adjust the coordinates and get the coordinates for the targets, which is exactly same as the geodetic network. We do have different methods for macro network. We start from establishing the macro network using triangulation. Prior to improvement in EDM and distance measurement, all the geodetic network used to be set out using the angles only or triangulation. So in this method we have two known points, say A and B, which the direction between these 2 points give us the x-axis. Obviously y is the orthogonal direction and z would be the line of gravity. So we can define the coordinate system based upon 2 control targets. And from that we can read through other marks. It can be floor and ceiling marks or wall marks, and we measure the horizontal and vertical angles from 2 stations to those targets. And once we've done that, if we choose the arbitrary x and y and z for the first point, then we can, using the least square adjustment, we can transfer these coordinates to other targets and points. Let's have a look at this picture here. So I have A and B as a known control point or measurement station. Say we find that these locations are the optimal distance to achieve the best accuracy. Then what we are doing, we are measuring to point 1 to 7, both vertical and horizontal. We also have the inverse scale bar. The reason for that is we don't have or don't measure any distances in this type of macro network. So we do need to have some kind of scale bar. So we know the distance for this scale bar. If we measure to these 2 points from 2 stations, we should be able to scale the network. Then if we give the arbitrary point or coordinates to 1, x, y, z, we should be able to get the coordinates for point 1 to 7 using the least square adjustment. Sorry for my bad handwriting. So hopefully that clears how we're going to establish the macro network using the triangulation. The next method is measuring the object point. In this macro network, the object point will be measured in a similar fashion. Probably we don't have the scale bar this time, and we use the least square adjustment to get the coordinates for the setup station, which is point A and B, and the selected point object that we put the targets, so we can have the coordinates of them and setup station. And if you know the coordinates of the object from the design, you can compare it with the one you measured from the coordinated network. And then we use the transformation, which we call it Helmet transformation. You don't need to know about that to compare those coordinates together. The only thing is the object in this method has their own alignment and coordinate system, so we are using that. It's not like the first one. First one we didn't have any alignment or coordinate system for the object. The last one is macro network using the angle and distance. In this example, we assume that we are using the instrument that can measure the distance for us, like a robotic total station. So we are measuring the distance and angles with the same approach. We don't need to have the scale bar since we are measuring the distance. The only thing we need to make sure that the distance and angle has the same precision or compatible precision, so you can't really measure the distance very precisely and then measure the angle with the precision, say 1 minute. So it's just not compatible, or it can't be integrated together. So it should have the same precision or accuracy. And then same as before, we use a transformation that we call helmet to compare the coordinates of the point that we just calculated using the least square adjustment and those measurements, and with the one which we have from the object design. Again, we don't need to know about the transformation at all at this level. We just need to know the procedure and steps needs to be undertaken. In the metrology, we do have different characteristics and symbols that you need to know, like there is a list of or table in the study book that you can look for and read, but I just copy paste some of them here, like straightness, flatness, like circularity, symmetry. So all of these can be defined, and there's a description. So I put a table. Please take time and read through the descriptions to be able to understand what we are going to cover from now on in this lecture and the course in general. There is no specific agreed classification for LSDM, or large scale dimensional metrology. The main division for them, it can be categorized in two different systems, centralized and distributed. I'm going through each of them in next few slides. We also have different categories based on the hybrid system, like both of them together, and different general categories that I'm going to explain that as well. The second type of the system are distributed system. The difference is in distributed system, you don't measure the coordinate directly, you rely on the interrelationship between the instrument and or the targets to determine the position. The example of that might be the photogrammetry method, that you're taking an image and basically you take and then you can get the coordinates of the point later on based upon the coordinates of the camera station. So this method can be named as one-to-many measurement rather than one-to-one. So you take an image once and then you can get the coordinates of the point all in one image. Another example would be the laser, LED or sonic system. Again, you can have the emitters that emit the signal or take the image in photogrammetry, and then it can get the coordinates later on based on the relationship between the camera station and the points in the images in this example. There are a number of other classifications. The first one is contact or non-contact. Is basically classified based upon that whether you use the target or you use the reflectorless measurement, like a laser, for example. It can be active or passive. Active system emit a signal whose reflection is measured to determine the distance. It's like a total station. You send a signal, the target reflects back the signal, and then you can measure the time of flight or the phase difference to get the distance. So this is the active system. But we do have a passive system like a photogrammetry that rely on the reflection of the natural or artificial light to illuminate an object, and the system image the object. We also have the portable, semi-fixed and fixed. Is pretty much obvious from the name. For generally speaking, portability is linked to calibration and datum establishment. Hence many distributed systems are considered as fixed, and they need to be calibrated inside and remain in those positions, so we don't call them portable, they're fixed. We also have the portable device like a laser tracker that generate or being portable, they can carry, they can be moved. So all these devices categorized as the portable. We also have the semi-fixed system. We also have the real-time and post-process. Again, real-time is obvious from the name. We get the measurement in real-time. Post-process can be like photogrammetry that you process the images later. We also have a probe direct line of sight. Direct line of sight is where you can measure the target directly. We also have the probe cable, which gives you an option to measure the area which is difficult to access or is not in your line of sight. We are going to talk about the probe cable later on a little bit more. Systems can also be categorized by their need for calibration. Generally, distributed system need to be calibrated in the site is very complex and time consuming because they're fixed in the site, but once you've done that, you don't need to do it for every setup. On the other hand, there are some systems that you have to establish the orientation, datum definition on each setup, like laser tracker or similar devices. So basically, they both have advantages and disadvantages. The next category is based on the distance measurement technology or procedure. We're going to discuss that later in more detail, but the critical factor is the safety aspect of a specific technique. Sometimes we can't really access the machinery because it's difficult to access or it's hot or it's dangerous. So depends on that. We can categorize the larger scale metrology based on the distance measurement technology. The last one is based on the precision and range. So obviously design tolerance determine the required metrology precision, and range is the function of the system you are using. So different systems have different range and precision that can be categorized based upon that. Measurement system instrumentation and operation in larger scale dimensional metrology can vary, depends on the purpose of the project. So it's basically fit for purpose, and then it can vary, depends on the limitation you have for the site, the physical size of the machinery, whether you are able to put the target on the machinery or there is some area that you don't have line of sight and you need to use probe or other instruments. So this basically vary the choices you have, and you have to consider all those limitations to be able to choose the right system for measurement. Precise alignment is very important in metrology. So that's why we have the whole section on that, and I'm going through the different instruments or tools which can be used to precisely measure the alignment. But let's start with alignment itself. What is alignment? Alignment is basically when you're checking the direction against a line of sight. You may check the horizontal or vertical alignment. I've shown you before, but you have a surface and then you have a reference line, which is the laser beam, or it can be any sort of line of sight, and then you measure the offset from your surface to this line, and if these offsets are equal, basically your surface is flat and is pretty much aligned with that line. But if you have a different surface, like if you say your surface it looks like that, and then you're measuring the offset, my line is not quite straight, but if you measure this offset, some of them are higher and lower, yep. So it means that your surface is not quite flat, so it can be used even for flatness and horizontality or verticality of the surface. So as I said, you can measure the alignment in respect to the vertical or horizontal plane. Alignment is basically the critical part of the subdiscipline of optical tooling in metrology. So by optical tooling, I mean that you're using the devices, they have the optical piece, or that's why we calling them optical tooling. So the example of using the alignment in industrial measurement, it can be a roller system where you have a printing rollers, like the example I've shown you before, that you have a roller and you have a reference line and you want to align your roller perpendicular to the reference line, and you put the instrument in different station obviously and turn it to 90 degrees from the line of sight, and then you can align the rollers. Another example is alignment of critical equipment components. This can be applied to generator and turbine system, where different parts needs to be aligned in exact or very precise angle. So in general, alignment is to measure the small deviation or tilt in angle, and we should be able to align the machinery in the very precise direction. The tools can be used to measure precise alignment are alignment telescope, collimator, autocollimator, precise levels, and different systems that I'm not going through them, I'm just mentioning them, but it's always good to know what are in the market. So let's start with the alignment telescope. As I said, we call it optical tooling. Obviously, it's always from the name. So if there is an eyepiece or optical element, that's why we call it optical tooling. It's pretty much like a telescope we have in theodolite or total station. The only difference is the optics here are very improved. As you can see, we can measure horizontal and vertical deviation up to micrometer. So there is a micrometer over there, and then we have a focus wheel which is very precise, and then we have a changeable eyepiece. I'm telling you why it's changeable, because sometimes they can remove this and put some camera to get the image processing rather than just optical or analog tooling. So don't worry about that now. I put a video on the study desk. If you're interested more, you can go and watch that video. It's very interesting and it's helping you to understand the concept more. Let's get back to here. So what alignment telescope does is just provide a line of sight for you which is not changing by the focus, and the optical tool we have here, it allows us to focus from 0 to infinity, and we also can measure the angular deviation of micrometer from line of sight, which is very precise. The second tool we have to measure the precise alignment is collimator. Collimator consists of a light source here, and then we have a diffuser or filters, and then we have a reticle focal plane, and the last one is we have the object lens here. So we have an object lens. So what's happening is the light source is emitting the light, obviously, or light rays, and it's passing through the focal plane. If you set a telescope at infinity focus, the incoming light passing through the focal plane is gonna come out as a parallel rays or light rays. So then you can basically use the collimator to project the image of a reticle along the reference line over a range of distance. That distance can vary. Now if you combine the collimator with an alignment telescope like the one we have here, then what you can do, because these lines are parallel, if they come through the object lens of the alignment telescope, and if you set the focal plane of here or reticle focal plane of here to infinity as well, so what's happening if your line of sight of this is the telescope, if the line of sight of the telescope is parallel to this light source, two reticles should be aligned together like the one we have here. So basically the lateral movement doesn't matter, or it's not really affecting the result as the lights are parallel, so it doesn't matter when it comes to the object lens. But if you have any tilt, it causing that two reticle or crosshair doesn't quite match each other. So then from the difference of them you can find out how much tilt or deviation you have from line of sight. This feature of collimator has many applications. One of the applications we already discussed, that you can align the roller or printing press rollers in regard to the line of the roller. So we have a line of sight basically set by the collimator, and then you put the instrument, turn it to 90 degrees at each of these stations, and then you can align the roller to be perpendicular to the control line of the rollers. Another thing is for testing the theodolite and total station. You can see on the right hand side how they are testing the total station angles to make sure that they can measure to the requirement accuracy or precision. The next tool we have for precise alignment measurement is autocollimator. It's basically combination of the standard telescope and a collimator. So two previous devices that I've already explained, if you combine them together, it's going to be autocollimator. The only difference here that you can see is we combine the illumination source and the telescope together. So this bit is the telescope bit, and this bit is basically collimator, and if you combine them together you can have the autocollimator. For autocollimator the principle is same. We have a light source, we have the light emitting and passing through the filters, is passing through the object reticle, and then it's basically splitting to two beams. One's go on the left hand side and one going to the right hand side, so you can have a reticle image. Actually you see two of them, two reticle, one from the object and one is basically going through the mirror and coming back or reflecting back from the mirror, and you can see two of them. Again, if they two of them are aligned together, it means that the mirror is basically perpendicular to the line of sight and you don't have any tilt. But if you do have any tilt, it's gonna be this slide here. You can see if your mirror has a tilt and it's not quite perpendicular to the line of sight, then there's a deviation of the angle, say by A, and then your light rays is gonna be deviated by twice of that angle, and then your two crosshairs or reticles not quite matching each other, which shows you the deviation that you have in, or tilt you have in your mirror, and is tilting by the angles. We do have two types of autocollimator. The analog one that you look through like an optical piece or eyepiece, and then you find the changes in the reticles of the from the object, and obviously the one is reflected back from the mirror. And we also have the electronic autocollimator that we use rather than have, if I'm going back, rather than have the eyepiece here, we have the camera. So what's happening, camera taking images, or is kind of a sensor, and this sensor, which CMOS stands for complementary metal oxide semiconductor image sensor, is basically sensing the image and find the difference between the two crosshair images by image processing software basically. The example of the application of autocollimation is shown here. You can see for point A to E in this picture, from A to E. We do have autocollimation here, so we set up the line of sight and then we can find a deviation from the line of sight for each of these stations, and actually the accuracy we can get is very good. We can have for optical or analog autocollimator, we can achieve the accuracy or precision of the half of seconds of arc, while for electrical is even better, is milliseconds or 2 milliseconds of arc, which is very good. So then if you have this one, and then you can also get the deviation whether from horizontal or vertical plane, as I said, for horizontal or vertical alignment, or for flatness assessment, which we can have a precise one, having set the accuracy for the optical, whether you're using optical or electrical system, you might have different accuracy. The last tool I'm going to explain is the precise level. It's very familiar for us. We all know about the level in surveying, but precise level has slightly different features from what you've seen in normal surveying job. So what we have here which is different, we have a parallel plate micrometer attachment. So you can see we have a micrometer drum and turn knob, and then we have a parallel plate here. So there's a new system on top of the normal level. So you have two eyepiece, obviously one for setting up the line of sight, and the other one also you're gonna adjust and even the line of sight or shift the line of sight. And then you need to have the precise level and precise rods and scales. So the rod we are using for this type of level is different from the normal level that we have in surveying. So the graduation on the rod is different, so you can read up to millimeter accuracy, which is very precise, or even better, sometimes to micrometer. A precise level as described is suitable for checking the flatness and horizontality. So we can use this for checking the flatness of the surface and horizontality of the surface. And if you have the very good target which has a micrometer reading or graduation, you can get the deviation from the horizontal to micrometer accuracy. I've covered the very common system. We also have other systems which can be used for optical alignment. The number of them is jig transits, auto-reflection techniques, dual telescope system, optical square prisms. That one is very cool. It's pretty much like what we have as an optical square for the normal surveying, but this is more for squareness and it's very precise. So you can go and search the name in the net and find the information for them if you're interested. If not, it's not going to be accessible and it's not going to be in the exam, I assure you.